Hello dear students, welcome you all for Power System Operation and Control class. Today we start with the module 3, which is having two parts. The first part in the third module is the mathematical model of ALFC. That is the continuation of your AGC only. Okay, in the previous classes we have seen the different governors, governor modes and how AGC works and all. Today we will go for the mathematical model of the ALFC. So that is automatic load frequency control. How a mathematical model works for this ALFC. So the mathematical model of ALFC can be easily done by the developing the transfer function model of the each element in it. The inputs of the ALFC element are the output power set point, that is delta P reference, and the change in the active power load, that is delta PL. The functional block diagram is as shown in this figure. You can see this figure. There is a one governor, one turbine, then the delta PM is there, that will be given to the summer, where the delta PL is there, that is the active power load change. Then generator load will be there, the speed is sensed using the droop, and it is once again given back to the summer. So this is what the functional block diagram of a ALFC. So now the thing is, what each block, whatever I have shown in this functional block diagram, each block we need to model it. So then only we'll come to know how exactly these things are going to work. So let us enter to first governor model. So this is the block diagram of governor model. You can see here. Here the output of the speed sensor omega is compared with the reference speed or omega reference. You can see here the output of the speed sensor omega is compared with the omega reference. You can see at this summing point, the speed sensor omega and omega reference is compared to produce the error speed, that is delta omega. So whatever is coming from this summer is the delta omega. That is a change in the speed or error speed. We have reference set point for the output. By adjusting the set point on a unit, its output can vary while holding the system frequency close to the standard frequency. The error due to difference between the actual power output and the reference set point is fed back to the speed regulation, or the transfer function equivalent diagrams are shown here. You can see these figures A, B, C, whatever is there. There is a transfer function equivalent figures. Okay, so here uh, uh, you can see three figures A, B, and C. The block reduction shown in the figure B, and the Tg is the governor time constant, and it can be see that depends upon the speed regulation R and on the gain of hydraulic amplifier Kg. So this is what our block diagram reduction of a block model of a governor model. So the main intention in this governor model is what? The main intention is what? Our speed sensed speed sensors output omega is compared with the reference speed, and the error speed is taken. Okay, now coming to the generator model. So generator model, there are two torques are acting on the generator. The shaft torque, that is due to the prime mover, and the electromagnetic torque, that is neglecting the losses. The shaft torque tends to accelerate the generator in positive direction of the rotation, and electromagnetic torque in negative direction. You can see in this figure. See, Tm, that is the shaft torque, is the moving in the same direction of the speed, and your electromagnetic torque T is in opposite direction. So the accelerating torque is given by Ta is equal to Tm minus Te, that we are knowing. From the Newton's law of motion, we have a for the rotatory motion we are having I alpha is equal to T, where I is the moment of inertia, A is the angular acceleration, and T is the net torque. So the equation we can written as I d square Tm by dt square is equal to Tm minus T. This you are seeing in string equations and all. Okay, how this one? Two torques are accelerating torque is equal to inertia, moment of inertia into the second order derivative of the displacement. Okay, where t time is the rotor angle, that is the displacement what I called, is now converted into angle measured with respect to the synchronously rotating reference axis. So I can write it as delta m is equal to theta m minus omega smt. Okay, where omega sm is the synchronous speed in radians per second and delta m is the angular displacement in radiations. So from the equation, the what we are have here, that is equation 3, I can write that d square d by dt square of delta m is equal to d by dt square of theta m. So both are same. So I can write it as instead of theta, I will use delta. That is I into d by dt square of delta m is equal to tm minus t newtons meter. So where omega m I is equal to is nothing but angular momentum or inertia constant. Omega m into tm is nothing but pm, that is the mechanical power input of the shaft, and omega m into t is nothing but the electric power output. We are knowing that is speed into the torque, so we will get the power. So instead of the previous equation 6, we will be having the equation m into d by dt square of delta m is equal to pm minus p, which is equal to p pa into pa, that is in watts. Okay, so here pa is the accelerating power, m depends upon the speed of omega m. However, since the deviation is speed limited, m can be assumed to be a constant. The value of m varies over a wide range depending upon the rating of the type of rating and the type of the generator. Hence, the another constant h can be used to specify the energy stored in the machine, where h is given by stored kinetic energy in megajoules at synchronous speed divided by machine rating in MVA. So h is also called as inertia constant. It lies in narrow range for different machines. So m and h are related as follows. We are knowing the how it is related. M is equal to 2gh by omega sm. Okay, where g is the MVA rating of the machine, in per unit m is equal to 2h. So once again we can rewrite the equation. So I will get the equation as 2h by omega sm into d by dt square of delta m is equal to pm minus p by g. So expressing the same equation, now we will get the g is the MVA rating of the machine. So we know that m is equal to 2h, that is. So equations are changes to 2h by omega s d by dt square of delta m, which is equal to pm minus p, which is nothing but pa per unit. So pm is the per unit mechanical power, omega s is the synchronous speed in the electrical radians per second. So p by 2 omega sm, which is that is, or pa is equal to accelerating power. So the now we will get a swing equation, that is change in the power. So expressing the speed deviations, so finally it will become d by dt of delta omega, that is speed change delta omega, is equal to 1 by 2h into delta pm minus delta p, that is a change in the mechanical power minus the change in the electric power. Apply the Laplace transform to this equation. So wherever t is there, that is becoming s here, because from the time domain to frequency domain using Laplace transform, delta omega of s is equal to 1 by 2 hs into delta pm of s minus delta p of s. So the same equation can be modeled in the given block diagram. You can see here, here delta pms minus delta ps, because both are given to a summer, it will become delta pm of s minus delta p of s, that is multiply with 1 by 2 hs, that will gives you the delta omega s. This is the mode of generator. Okay, model of the generator, how the generator model is works. In this figure we can conclude it, or this is a generator model, how we are going to model generator using the different equations. Okay, in the next class we will see regarding the load model, how a load model is modeled, because in the first part of the ALFC is the governor model. No, governor is there. Before that we are having a generator and load here. See, so that is the generator model we are already done. Next is the load model. After that we will go for the different models of different things, which is there, turbine is there, and then governor is there. All those things we will see one by one. First thing is generator is modeled. Now next generator plus load is there. Next in the next class we will see the